Hello everyone, in this video I'll talk about partial fractions decomposition, which we eventually use to integrate proper rational function. Alright, so the first question arises, what is a rational function? A rational function is any function that is ratio of polynomials. A proper rational function is when the order of polynomial in the numerator position is less than the order of the polynomial in the denominator position. What does this mean? So this means, let's say if we have something like x minus 1 over 3x squared minus 9. So what is the degree of polynomial that is on the top, or that is in the numerator? So degree of this polynomial is 1 and degree of the polynomial that is in the denominator is 2. So this is called a proper rational function because the degree of polynomial in the numerator is less than the degree of polynomial in the denominator. On the other hand, if we have the same order of the polynomial in the numerator and same order of polynomial in the denominator, or the degree of the polynomial in the numerator is greater than the degree of polynomial in the denominator, then we have an improper rational function. So one of the examples would be, so in this one we have order 2 in the numerator and order 2 in the denominator. So this is an example of improper rational function. You can think this in terms of numbers. So if you have 2 over 5, so the numerator number is less than the denominator, and we say that this is a proper fraction. But if we have something like, let's say 5 over 2, so this is an improper fraction, and we can write this as a mixed number. So similar thing goes pretty much in our rational functions. So if the degree in the numerator is less than the degree in the denominator, we say it's a proper rational function. If the degree in the numerator is same or is greater than the degree of denominator, then we say we have an improper rational function. So just like in numbers, if we have an improper fraction and we try to convert that into mixed number, we can do, or we can write this as 2 plus 1 over 2. So we do the exact same thing in case of rational functions. So if you have an improper rational function, you can write that in terms of proper rational function using your long division. I'll do a quick recap of long division here. So here we have this improper fraction. So degree is 3 in the numerator. So we put this term inside the division, and x squared minus 5x plus 6 would be our divisor. And then we ask ourselves a question that what should I multiply x squared in order to get x cubed? And the answer is x, or in other words, you can divide x cube over x square and see where you get x. So we should multiply x square with x in order to get x cube. So x cube, and then negative 5x times x is negative 5x square, and then we have plus 6x, and then we subtract. So we subtract throughout. So x cube minus x cube is 0, negative 5x squared plus 5x squared is 0, and we are left with negative 6x here. And then we ask ourselves question, by what should I multiply negative 6x in order to get x squared? So there is nothing, right? Because we got the degree 1 here, which is less than degree 2. So it's like our remainder. So this is a time when we need to stop. So we notice here that we get a degree which is less than the degree of our divisor. So this is the time when we stop. So this is our remainder. So now we're going to do the exact same thing that we used to do in with our numbers in long division. So we write our answer as quotient plus remainder over divisor. So we're going to do the same thing. So it means this original fraction is equal to quotient, which is x, plus remainder, over divisor. So x square minus 5x plus 6. I always tell my students, so we start from here and we go clockwise direction. So quotient plus remainder over divisor. So now we notice that here we have our improper fraction that we change into a proper fraction, because for this part, for this one, our degree in the numerator is less than the degree in the denominator. So this is our proper fraction rational function. So let's try one more example. If you don't have a proper rational function, so you can always convert in proper rational function to a proper rational function by using long division method. So again, here we have the degree in numerator is 4, the degree in denominator is 1. So we set up our long division. So divisor is x minus 3, and then we set up our long division. So first we think in our mind, what should I multiply x with in order to get x raised to power 4? It means we need another 3 copies of x. So x cube. So x times x cube is x raised to power 4. So negative 3 times x cube is negative 3x cube. And then we subtract. So here after subtraction, we see that we get x minus x raised to the power 4 minus x raised to the power 4, which is 0 again, 0. And then we bring another term down, so 2x cube, x squared comes down. And then we think, what should I multiply x with in order to get 2x squared? So answer is 2x. So 2x squared, and then 2x times negative 3 is negative 6x. And again we subtract. So 2x squared minus 2x squared is 0. So negative and negative. So we get positive 6x. And then we bring another term down. So we get negative 7 here. So now we think, what should I multiply x with in order to get 6x? The answer is plus 6. So we get 6x. And then negative 3 times 6 is negative 18. And we subtract. We get 18 minus 7, which is 11. And now we got the degree 0 here, and we have a linear term here. So this is the time when we stop. This is our remainder. So 11 is our remainder. Thus, we can write our improper rational function as, so proper rational function, quotient plus remainder over divisor. So always start from the top and go clockwise direction. So quotient plus remainder over divisor. So this was plus 11 over x minus 3, and this is our proper rational function. So anytime if you have an improper rational function, so make sure you convert that into a proper rational function first, and only then you can proceed to partial fractions decomposition. So what is partial fractions decomposition? So previously we know that in algebra usually we combine fractions into a single fraction by means of addition. However, if we wish to integrate an expression that contains rational fractions in which both numerator and denominator are polynomials, so it is often useful to reverse the process of addition, and that reversing the process of addition is known as partial fraction decomposition. So that means you have a rational fraction and you are converting these into sum of simpler fractions which may be easier to integrate. So we are decomposing a big rational function into two simpler rational functions. So we're going to learn how to do this. The following table tells us how we decide upon the denominators of, when we split the fraction into sum of two fractions, how we decide on the denominators. So if you have a factor in the denominator, so in the original fraction ax plus b, you have a linear factor, then the term in the partial fractions decomposition would be of the form, so in the denominator you have ax plus b, and on the top you get a constant. If you have nth power of a linear factor, then we set up the terms in the decomposition as follows. So a1 over ax plus b, a2 over ax plus b square, an over ax plus b raised to power n. So basically we think about all the factors of ax plus b raised to power n. So this is a factor of ax plus b square is a factor of ax plus b raised to power n, and so on up to nth power, right? So all these are the factors of ax plus b raised to power n. So we get one term corresponding to each of these factors. So if the factor is linear, so on the numerator you get 1 degree less. So you get a constant number in the numerator. What if you have a quadratic factor in the denominator? So in that case, in the numerator, we're going to have a linear numerator. So we're going to have something of the form ax plus b. Similarly, if you have many copies of ax square plus bx plus c raised to power n, so basically you have nth power of a quadratic expression in the denominator. So for this one, we're gonna have different terms with different denominators. So first would be 1 power, then we have second power, 2 power, and 3 power, and so on nth power. And all the numerators are gonna be of the form ax plus b. So that's how we're gonna decide our terms in the partial fractions decomposition. So this is gonna be our setup. Once we have the correct setup, we're gonna figure out the values of our constants a's and b's, etc. So the gist is whenever you do the setup, so for each term, the power in the numerator would be 1 less than the denominator. So if you have linear in the denominator, you're going to have a constant in the numerator. If you have a quadratic in the denominator, you're going to have a linear in the numerator. So 1 power less. And depending on if you have nth power of a linear term, linear factor, so you have to create fractional term for each linear factor present. So for all the degrees less than equal to n. Similarly, if you have a quadratic factor and the degree of quadratic factor, you have to create a fractional term corresponding to each quadratic factor present. I'm going to show you how to set up the terms. So for practice, so I'm just going to use one of the methods in the table given above. So we don't not gonna calculate constants at this point. So I'm just gonna show you how to set up the terms in partial fractions decomposition. All right, so in the first one, we have three linear factors in the denominator, and out of those two have some degree. So what we're gonna do, so x minus 2 whole square. So this has two factors, so degree 1 and degree 2. So it means corresponding to this, we're going to have two terms with these denominators. And then we have this one. So x minus 3 whole square, so degree 1, degree 2. Again, we're going to have another two terms, so 1 over x minus 3 plus something over x minus 3 square. And lastly, we have just single linear term. So we're going to have another term with denominator x plus 9. And now, since all these are linear factors, so we're going to have some constants on the top. So a over this, b over this, c over this, d over this, and e over this. So that is our setup for the partial fractions decomposition. And I'll show you how to calculate a, b, c, d, e later on. So let's take a look at the next one. So next one we have a linear factor, cube of that, and a quadratic factor, square of that. So first thing we notice that here we have degree 3, so it means it's going to have three factors: 3x plus 2, 3x plus 2 square, 3x plus 2 cube. So we're going to decompose, so we're going to have three terms corresponding to this factor with square and then with cube. For the quadratic one, since the degree is maximum power, like is 2, so it's the whole square of that. So we're gonna have x squared plus 2x plus 1, and also we're gonna have x squared plus 2x plus 1 whole square. So we're gonna get two terms corresponding to these factors, and plus x squared plus 2x plus 1 whole square. And as discussed earlier, what should be on the top? So for any linear factor, we're gonna have the constant terms. For any quadratic, we're going to have the terms of the form something x plus something. So dx plus e. Similarly, fx plus g, where a, b, c, d, e, f, g all are constant. So this is how we set up our partial fractions decomposition terms. In the next video, I'll show you how to calculate these constants. So please do watch the next video as well. Thanks for watching.